So this is chapter 9 on rotation. We're going to talk first about angular displacement. Angular displacement is just what it says. It's how far around the 363 degrees you are in angles. It can either be by revolutions, by degrees, or by radians. Generally, the SI unit for this is radians. So we measure the distance you go around a circle, and it can be 360 degrees, it could be 720 degrees. So that tells you basically how many times you've gone around. Angular displacement is represented by the letter theta, and arc length, which we're going to talk about also, is represented by S, the letter S, and that's in meters. So we'll talk a little bit about radians. Radian is, well, 1 revolution is equal to 2 pi radians, which also is equal to 360 degrees. You could use these three as your conversion factors between degrees, radians, and revolutions. The SI unit, again, is radians. The little diagram that you see down here kind of spells out the fact that theta is, you got a little bit of a glare on that. Theta is equal to S over R. R is radius, S is arc length. Of course, we're going to talk next about omega, which is the angular velocity. That's how many radians per second you're moving. And that omega is equal to the tangential velocity, which would be kind of like if a particle or a bug flew off, how fast would it be going at the time it took off? And you can see theta is marked there as the angle. So much like translational or linear velocity acceleration, some objects are also spinning. Some are moving and spinning. So, it gets a little complicated when you have all that happening at one time. We define angular velocity as the change of angular displacement in a unit of time, or radians per second, which would be the SI unit. We show angular velocity with the letter omega, which looks like a curved W. And, of course, omega is equal to theta over time, delta theta over delta t. And here's kind of our calculus version of that. Angular acceleration. And, of course, we've got all these analogs for linear and angular, just like we had regular acceleration. Angular acceleration is how the velocity is changing, the angular velocity. And this is represented by the Greek letter alpha, which looks like a fish swimming to the left. You can see on the little diagram here that A is equal to the change in omega over the change in time. So rotational and linear analogous equations, look over these. These will be on your possibly useful page on my test. You can see that for each of the linear equations on the right, there is a rotational motion equation on the left. And you should look at these. You should be familiar with how to use those already. You'll get some problems that basically, how do you do these? You write down the things that you have in the problem, the variables you have in the problem, and then go shopping for an equation in this list that fits the bill, and then do the algebra to shuffle them around. Angular direction. So a couple of things. First of all, angular displacement, velocity, and acceleration, they're all vector quantities, sometimes called pseudo-vector quantities. Because it's not like the straight line type thing that we've dealt with in the past with linear motion. The positive direction is counterclockwise, and that's important that you be consistent on that because that is the standard. Okay, so also talk about torque in this chapter. Torque is like force is in linear motion is a push or a pull. Torque is a twist. And to solve for torque, the easy version of that would be the force times the perpendicular force times the radius, or the force times the lever arm. Lever arm would be like a wrench or like any type of long distance. Could even be a round object. It's the distance from the center to the edge, like on a basketball. You would draw a radius, and then the perpendicular to that, the tangent to that, would be the force. So force, no matter how much, doesn't really apply unless it's a right angle force. So if you have a force at a 45-degree angle, only only part of that is being applied. So you're going to have to do some trig with sine and cosine to figure out what the right angle version part of that is. The general equation that works for every problem would be tau, which is what we use for torque, Greek letter for T, equals r, the radius, times the force, times sine of theta. You can see how this is drawn in that diagram, and it's only that part, the perpendicular component, that counts for torque. The units for torque are Newton meter. That's the SI units. Newton's second law is F equal ma if you're in translational or linear land, but in rotational land, it's tau equals I alpha. In other words, torque equals moment of inertia times angular acceleration. So this equation a lot of times will be combined with torque equals force times distance, which is the torque formula to solve problems. So basically you could set force times distance equal to I alpha in some of the problems, and that'll help you solve them. On page 265, table 9.1, there's a table of the different shapes, and these are the formulas that you use to solve for I, which is moment of inertia. If you want to get a feel for what moment of inertia is, spin a bicycle wheel and hold on to the axle. That will give you a feel for moment of inertia. Different shapes have different moment of inertias, because if you have a lot of mass on the outside, that's different than if you have a lot of mass on the inside. If you have a basketball, which is a spherical shell, that's different than a solid sphere that has mass throughout the whole measure. If you have a bar that you're spinning in the middle, in the center, that's different from spinning it on one end around an axle. So look on page 265. Those are the formulas that you'll use in order to solve for moment of inertia. This is a chart that looks similar to that chart in your book. And I'll give you the chart in your book. You may not have that on the AP test. We'll need to look at the possibly useful information. But I is moment of inertia, big M is mass, L or R is the distance or the radius. So that covers that first couple of sections on Chapter 9. Read through it, solve some of the problems in the sections, and then solve the homework problems. And we will continue on next time and talk about rolling motion and kinetic energy with rolling objects without slipping, with and without slipping.